fundamentals of data science subject. The topics which need to be covered from unit 4 are mathematical modeling, philosophy of modeling, taxonomy of models, baseline models, evaluating models, evaluation environment. So we'll have a brief overview of all of those. So in the word mathematical models, we have model as one of the word. What model indicates? It's a process which encapsulates information into a tool, and that tool will forecast and make predictions. Now we'll be trying to understand model design and model validations. So what is the philosophy of modeling? Let us take Occam's razor philosophy of modeling. What he says: the simplest explanation is the best explanation. So he says, given two models which are doing equally accurate job of making predictions, we should opt for the simpler one as sounder and more robust. It is more likely to be making the right decision for the right reasons. What this Occam's razor philosophical principle is based on is simplicity, right? So when he says simplicity, he is speaking about reducing the number of assumptions. He speaks about minimizing the parameter count. So he says if there are more parameters, or statistics says if there are more parameters, then model will be memorizing the entire training set instead of generalization. Any model which does predictions or classifications or recommendations, the it's a learning model and it has a machine learning as its crux. So it should have a generalization principle or approach. So this will not be possible if the model gets overfitted. And what is the meaning of overfitting is a model tries too hard to achieve accurate performance on its training data. Overfit models perform extremely well on training data, but less accurate on independent test data. So what Occam said is simplicity. When he says simplicity, he says generalization, or machine learning philosophy says generalization. Uh, but let us say if it is the model is simple and the performance is poor, then it is not a desired quality. Say for example, you have deep learning, which is a very powerful technique, and it has millions of parameters. It has the risk of overfitting, but still deep learning models are performing extremely well. So it means we have to select the trade-off between accuracy and simplicity. Let us go back to the two terms which we have discussed previously: bias, variance, trade-off. What is bias? Bias is an error. What is variance? Variance also is an error. But bias is an error from what? Incorrect assumptions built into the model. Say for example, restricting an interpolating function to be linear instead of a high order curve. What is variance? It is sensitivity to fluctuations in the training set. Okay, say for example, you have sampling or measurement errors in the training set. This is noise which introduces variance into the resulting models. So bias is an error which leads to underfit models. Variance is an error which leads to overfit model. There's a discussion about Nat Silver's take on many aspects of models. And who is Nat Silver? Nat Silver is a well-known author of books like this, On the Edge, The Art of Risking Everything, or By the Signal and the Noise, Why So Many Predictions Fails. As well, he is very well known for that predictions. Say for example, if I look for Nate Silver predictions, he predicted elections, he predicted many other things like baseball games, kind of. So basically, he is a well-known statistician who does predictions well, whose predictions are accurate, kind of thing. So, what is Nat Silver's take on the entire modeling thing? Okay, so as it is mentioned here, he is a well-known face in data science, Nat Silver. He does his election forecast on this 538.com. So in 2008 he was accurate, in 2016 he was accurate, and he wrote various books like Signal and Noise, Why So Many Predictions Fail But Some Don't. So according to him, the principle for effective modeling are this. First one is think probabilistically. So for example, you are making some forecast. They should not be concrete statements, but they should be probabilistic. Say for example, if I forecast that Trump has 28.3% chance of winning, so this is more meaningful than categorically stating that Trump will lose, as the real world is an uncertain place and successful models recognize this uncertainty. So if you're forecasting numerical quantities, they should not be single numbers, but they should be probability distributions. You have standard deviation sigma, you have mean prediction mu, which will be describing the distribution, if the distribution is assumed to be a normal distribution. So most of the machine learning techniques will be giving probabilistic answers only, including logistic regression, which provides a confidence along with each classification it makes. So if you forecast it and there is a new information, there is a live information, you change your forecast as per the inputs of that live information. So you should, as a data scientist, you should be open to changing opinions in response to new data. Dynamically changing forecasts provide excellent opportunity to evaluate models. Look for consensus. What is a good forecast? A good forecast comes from multiple distinct sources of evidence. You can employ Bayesian reasoning. So you know Bayes' theorem has multiple interpretations. So basically it is a way to calculate how probabilities change in response to new evidence. Here you can see P A bar B is equal to P B bar A P A P B. Here P A and P B are the prior probabilities. You have hypothesis A bar B of the event occurring A. So this is the probability formula. This is the Bayesian formula which can be applied. Coming to the taxonomy of models, basically it is speaking about types of models. The first type of models is linear versus non-linear models. Say for example, linear regression is there. It's an example of linear model where we have the linear relationship of y is equal to ax plus b, where y and x are the variables, y is the dependent variable, x is an independent variable. But generally the world is not linear, so you may go for high order polynomials, logarithms, exponentials, and basically what we will be doing there is we are trying to fit the coefficient there. Okay, we may not get the best possible fit. Say for example, you have deep learning methods which are based on neural networks. Though you cannot optimize much there, performances are good. But still linear models have their own benefits. They are understandable, easy to build, avoid overfitting on modest size data, and they follow Occam's razor principle. Simplest explanation is the best explanation. So this is the Yeah, under taxonomy of models, what we are discussing is model types. The first one is linear versus non-linear models. The second one is black box versus descriptive model. Black box models, they'll be kind of telling nothing about the system, how it works, while the descriptive models will be explaining, telling what it is doing, how it is doing, what decisions it is making. Say for example, linear regression is a descriptive model. Say for example, your decision trees, which path you are going to follow, decision tree makes us that possible. Even black box models, which are, say for example, deep learning models, neural network based models, they are extremely effective. But they're opaque. They don't speak about the system, how it does, why it does, whatever it does. First principle versus data driven models. Uh, First principle models employ full weight of classical mathematics like algebra, geometry, calculus. The model might be a discrete event simulation, while the data driven models are based on observed correlation between input parameters and output variables. So here what happens is the same model may be used today for one purpose, tomorrow from some other purpose by changing the data sets. We also have ad hoc models which are built using domain specific knowledge. But basically, best models are a mix of both theory and data. Then you have stochastic versus deterministic model. The moment we use the word stochastic, randomness is added there because stochastic means random. Okay, so say for example, you are adding probability into logistic regression, Monte Carlo simulation. You are being stochasticity. So what properties it will be having? The probability value will be between 0 and 1. The sum of those probabilities will be 1. Rare events do not have probability 0. The next models are flat versus hierarchical model. So with hierarchical model, what happens is evaluation happens in a logical and transparent way. Your hierarchical models are descriptive. So how I build my hierarchical model is I'll be decomposing the problem into subproblems. If you take deep learning models, they are the example of flat as well hierarchical models at the same time. The next models are baseline models. Baseline models are the simplest models. So more sophisticated models are derived from the baseline models. So any data science model, what it does, either it does classification or it will be doing value prediction. Say for example, classification, whether he is a man or woman, whether he has cancer or not, whether the mail is spam or not, such kind of things. The representative baseline model for classification can be uniform or random selection among labels, most common label appearing in the training data, most accurate single feature, somebody else's model, or clairvoyance. If I'm using baseline model for value prediction, uh, we may use mean, median, linear regression, value of the previous point in times. Now I want to evaluate my model. How do I evaluate my model? I can make use of confusion matrix like this, where I have the actual class and the predicted class. It's kind of actual results and the predicted results. So, and there is a relationship which this confusion matrix is true. The results are true, the predictions are positive. The results are false, the predictions are negative. The results are false, the predictions are positive. The results are true, the predictions are negative. So this brings a confusion matrix if it's a binary classifier. So what I am using for evaluating the models, I'll start with the confusion matrix. Then I'll go with this confusion matrix and contingency table. And as I just mentioned, what this Components of confusion matrix are true positive, true negative, false negative. Uh, and the literal meaning is same also. Okay. Uh, if the item is positive, it is labeled as positive. If the item is negative, it is labeled as negative. The prediction is negative. Sorry, the item is negative while the actual thing is positive. It is called as a type 1 error, while the next one, false negative, is called as a type 2 error. The other evaluation metrics which can be used are accuracy, precision, and recall and F score. So this is the formula for accuracy. True positive plus true negative divided by true positive plus true negative plus false negative plus false positive. This is the formula for precision. True positive divided by true positive plus false positive. This is the formula for recall. True positive divided by true positive plus false negative. And F score, which is also called as F1 score, it gives the harmonic mean of precision and recall. So the formula for that is 2 multiplied by precision into recall divided by precision plus recall. So we'll stop here as of now, and the rest of the point topics we'll cover in the next session. Thank you.